Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave, episode 736 to be precise. This question today comes from K6MIL, Pedro Marias, and he says, I read a lot of anecdotal commentaries about the relative efficiency of magnetic loop antennas to wire dipoles. Is there any scientific information to factually or mathematically compare the two types of antennas in ham radio frequencies and equivalent environmental conditions? Not really. My edition, the 22nd edition of the antenna book, does not detail enough information to make any transmission efficiency comparisons. Pedro, there are not any real good mathematical formulations from fundamentals. You could construct some, but the problem is that when you construct a mathematical model of an antenna, you have to make so many assumptions that it doesn't necessarily match with reality. Even if you go into something like EasyNEC or 4NEC2 or any of those popular modeling programs, they're going to model it. They're not going to create a mathematical representation of that particular antenna. But I will show you what they do and how they do it and why it works and the difference between the near field and the far field, and also the efficiency of an antenna in terms of radiation resistance. So let's dive in. Now, if you're going to model an antenna, say a center-fed dipole, the way the modeling software works, it breaks this into pieces. And usually the more pieces, the more accurate, the better. Okay. Now, it takes each one of these pieces and treats it as a tiny antenna. And it puts out waves like this. And this one puts out waves like this. And this one puts out waves like this. And it takes these and sums them up at the beginning of the far field, which is anywhere from 1/3 wavelength out to, depending on the gain, it's a function of the gain, to if you've got a parabolic antenna and microwave, it could be as many as 20 to 200 wavelengths out, but we're not worried about the microwave right now. We're worried about just an HF antenna. So what happens is you sum these. This is why it takes a while to model an antenna. You sum these up and see what it gives you in terms of a wavefront in the far field. Now, what is the difference between the far field and the near field? The far field is what we're used to. You've got an antenna here, okay, and you've got wavefronts out here going away from it. Well, as you get in near this thing, you get all these little pieces forming their own wavefronts, and it looks like a mess. And then as you get further out, you start to see more of the wavefront type action. This is called the near field. And is there energy in the near field? Absolutely, there's energy in the near field. And the problem is that each atom, each electron on there acts like a little antenna. And so they all overlap with each other to create this mess right here, which sorts itself out to the point where you get in the far field. Okay, you've got definable wavefronts out here. And this is how the antenna is modeled. It's heuristic, obviously. You create a model of the antenna, such as in a program like in, let's see, 4NEC2, or what was the name of that other one? Can't remember. Easy NEC. Easy NEC. I use Model 6 Plus. This uses a piece of software called the National Electromagnetic Code number 2. It is a piece of software a simulation software that was developed for the Department of, I think the Department of Defense some years ago. Now there is an NEC4, but it's proprietary. You have to pay a license for that. NEC2 is in the public domain. So the point being that to determine what the far field of an antenna looks like, you need to model, you know, like if you've got what is this? If you have a dipole like that, a folded dipole, you know, you model it and you discover what the patterns are. And you get 2 patterns that you can look at. You can get a 3D pattern if you want, but they're hard to see. But if you look at this on the horizontal edge, you get a elevation angle that comes out of here because ground is important. And if you look at it from the top, you get a, here's a circle, and you might get something that's broad here, a little less here. And so that's the, looking down at the top of the pattern for a dipole, you can see that if the dipole is this way, it tends more toward broadside than it does out the edges. Now your question has to do with mag loop. To do that, I want to introduce 2 terms. Radiation resistance, R sub R, is radiation resistance. Now, the thing about radiation resistance, this is the equivalent conceptual resistance that actually dissipates the power in the antenna. Then there's another kind of radiation called ohmic resistance. And the thing about ohmic resistance is this actually is the heat loss in the antenna. So if you look at your antenna, you've got an antenna here. I'll just show it from the end. You've got the equivalent of a radiation resistance and an ohmic resistance. And then you've got whatever, I'll just put it as a box here, whatever reactance you have. Okay? Radiation resistance is the equivalent of what you would transmit. Okay? This is for energy, we'll say lost, as electromagnetic field. This is what actually excites the radiation of the electromagnetic field. The ohmic resistance is heat. That's just, you know, warming the bird's feet as they sit on your antenna. Now, what we want, obviously, is for the ohmic resistance to be as small as possible and for the radiation resistance to be up very near the overall antenna impedance. If you look at this, you've got R plus JX, where X is the reactive part and R is the resistive part, which is the sum of these two is this resistance. Now, in a dipole, it is very easy to build a dipole where the ohmic resistance is about 1 ohm max. You know, if you're using 14 gauge wire, you've got even less than that. And your radiation resistance is around 50 ohms. Let's just take that as a common for the dipole, your standard dipole. You've got some ohmic resistance, which is not much, and you've got your radiation resistance around 50 ohms. So if you apply voltage to this, the voltage, we'll use voltage here, the voltage across this will be much smaller than the voltage across this, and it will radiate very well. Okay? Now let's take a look at your mag loop. Your mag loop, the magnetic loop has got a capacitance in here, and it's fed by a small coupling loop, and this is where the coax attaches. Okay? Now, you tune the antenna to resonance by tuning that capacitor. And this capacitor has very high voltages across it, low current, almost no current. Down here you have very high current, almost no voltage. Now the problem with this, with a small HF loop, is that the radiation resistance is very small. Okay, it could be an ohm or 2 ohms max. It could even be less than that, okay? So if you have normal ohmic type resistance in here, the R ohmic runs the risk of being larger than the radiation resistance. And when that's true, if these are equal, half of your energy is radiated as heat, the other half is radiated as electromagnetic waves. So the design objective in a magnetic loop antenna, and I point out that mag loop is a misnomer. It's a small HF loop, often called a mag loop. I'll call it a mag loop because that's what everybody else does, but note that that's a misnomer. Okay, so if the ohmic resistance is greater than the radiation resistance, you will lose more of your transmitted energy as heat radiating away from this thing, okay, than you will actually transmitting. So mag loops, good mag loops, go to great lengths to keep the ohmic resistance as low as humanly possible. Now I'll talk about MFJ's loop, for example. In MFJ's loop, they use a piece of copper pipe about 1 inch in diameter, and that runs around in the loop. So it's got a lot of skin area, and this skin area is what actually conducts the electricity. Okay? So this gives a very, very low ohmic resistance. And then when it comes to the capacitor, they actually bring in the tube, kind of flatten it, weld it, it's heliarched right there, to the stator plates of the capacitor. These are heliarched, okay, there, for the absolute minimum possible ohmic resistance. And then you have plates in here which turn, okay, and they come in and out of that. And then on the other side, you have more capacitive plates which are heliarched onto their support and then heliarched to the cable. Why heliarched? Because it's welded and it's aluminum. Using aluminum to weld aluminum, you need an inert gas to cover that while you're doing that, otherwise it will oxidize like crazy. So heliarc is short for helium arc. Now, helium is actually a fairly rare gas, so they're doing it now with other inert gases, like, for example, neon or something like that, that are also noble gases and don't react. And that way you can weld aluminum to aluminum. Okay, so the whole antenna is going to have a radiation resistance that may be 1 or 2 ohms, and then you have an ohmic resistance that is some fraction of an ohm, or 100th of an ohm, or something like that, so that the radiation resistance is much higher than the ohmic resistance, and that way the antenna can radiate rather than just sort of heat up the environment. Okay, so this is what you have to do. Now the actual tuning to resonance is done with the big capacitor that's in there, and then you have this coupling loop right here, which is actually connected to the transmitter line. So this sees 50 ohms when this is tuned properly. So the net of this is you have to get this thing tuned so that you get very high circulating currents in it. You can get thousands of volts across that capacitor, very heavy circulating currents, and in order for the thing to work properly. So if you look at a mag loop antenna, a really well-built one, you'll see that the actual loop itself is made of something pretty sturdy. A lot use LMR 400 and use the coax shield in that for this. The MFJ loops and some other loops that I've seen actually use aluminum pipe or copper pipe even, and do what they can to make sure that the ohmic resistance is as tiny as possible. So I hope that helps give you a few of the design considerations for mag loops. Magnetic loops are so tightly bound to their resonance frequency that if you move more than a few tens of kilohertz away at the lower bands, or at the higher bands, or just a few kilohertz away at the lower bands, you'll find yourself out of tune, okay? And so magnetic loop antennas do work, and they do the same thing there. If you can get the radiation resistance high enough compared to the ohmic resistance, most of that energy will in fact be radiated. And my personal experience with them is they do about as well as a dipole, and they don't have to be quite as high. So they are somewhat directional because in the direction perpendicular to the loop, by the time you work through all of those far field calculations, you find there's not much energy on the axis that goes through the loop. So Pedro, I hope that helps. There you have it. If those watching like this channel, I really ask you to subscribe. Subscription is simply your vote of confidence to YouTube that this is a channel worth watching. Also, if you'd like to help me bring you more of these videos, please throw a little something into the channel funds. You can go to dcastler.com/support, and there are several ways. The tip jar is right there. You can put money in one time just with the tip jar, or you can do a recurring tip on PayPal, or even better, join and become a patron via Patreon. And Patreon is a recurring type of a thing. So thank you all very much. Until we next meet, 73.